Warm.
Yeah, very well.
Have a big mouth.
And I'm nice fishing. And a child.
Yeah, no, my safety.
Okay, so today we're going to start out, now that we understand how air moves in and out of our lungs, that's our pulmonary ventilation. Now we're going to think about some additional factors that affect that process, right? So we already know that we're looking for a pressure gradient across the lungs, comparing atmospheric pressure to intraalveolar pressure in order to determine which direction it's moving. We know we have our intrapleural pressure as well. So we have a pressure across the wall of the lung, across the alveoli, our transpulmonary pressure that allows our lungs to expand with the chest wall. Now we are going to think about some familiar words, compliance and resistance, and how they're affecting this process. So just a reminder, compliance and resistance, we spoke about a little bit as we spoke about the cardiovascular system, but these are just properties of the world. These are physics concepts, kind of. They're going to affect our lungs as well. So we're going to think about how the compliance of our lungs, so properties of that tissue, are going to affect how much air we're able to get into our lungs and how easily. We're going to think about our airways, which are just a series of tubes. So their resistance is also variable, just like we saw resistance in our cardiovascular system was variable, specifically in those arterioles. So a reminder, we're going to start with compliance. I'm just going to remind you that when we're talking about compliance, we are talking about a relationship between volume and pressure. Okay? So relationship between volume and pressure. When we say something has high compliance, like a vein, what we're saying is that we can fit a lot of volume for just a little bit of a change in pressure, right? So we're saying high compliance means a lot of volume for just a little bit of pressure. Whereas when we say something has low compliance, we're saying that just a little bit of volume is available for that pressure, and just a little bit of volume can raise the pressure really high. That's what we talked about when we were looking at our veins and arteries. And when we're thinking about compliance in the lungs, we're still thinking about this fundamental relationship between volume and the pressure across a wall of something, now that we're talking about our lungs. Okay. So when we talk about lung compliance, and I've just kept that little diagram for us in the corner so that we can look at it while we look at the words. When we talk about lung compliance, we can think about it as how easy it is to stretch the tissue of your lungs. So phrasing it that way, hopefully that makes you realize that we want our lungs to be pretty easy to stretch, right? We want breathing to be easy, right? We want our lungs to be highly compliant, right? So the reason for that, right, is you want to get in lots of air, right? You want lots of air in your lungs, high volume, but you don't want to have to exert all that much pressure in order to get there, right? So if to get that volume, you had to create big changes in pressure, that would mean you're breathing pretty hard, right? Like, right? Easy breathing is just small changes in pressure. And you'd like to get as much air as you can during that process. So it's all about this volume pressure relationship. Okay. So larger lung compliance means it's easier to inspire, so easier to breathe in specifically. And you only need a little bit of a change in that transpulmonary pressure to bring in any given volume of air. So that transpulmonary pressure, remember, we were talking about our lungs sitting in our chest, draw that in red, right? Okay, and we're talking about our transpulmonary pressure as that pressure crossing the wall of the lung to the chest wall. This is our intrapleural space, right, where we have this intrapleural pressure. because we have fluid in this sac that's surrounding the lungs. We compare that pressure to the pressure in the lung itself, so in the alveoli. So our transpulmonary pressure is subtracting those two from each other. So subtracting our intrapleural pressure, so the pressure in this space, from the pressure in the alveoli there. So this transpulmonary pressure, we do refer to as a distending pressure, which was a term we could have used about the vasculature, our arteries and veins as well. It's a force across a wall exerting like a pull or a push, kind of. So what we're saying here is that we only need to change that intrapleural pressure, that alveolar pressure a bit in order to get enough volume moving into the lungs if we have high compliance. However, if we have low compliance, we're going to have a much greater transpulmonary pressure, so pressure across that wall that we're going to need in order to get that same amount of air. So I'm hammering home that you can imagine that there are diseases, for example, that can affect lung compliance and therefore make it more difficult to breathe in air, right? That's fundamentally kind of why we care about this. So there are some other trade-offs here as well. So we do know that the lungs bounce back after they expand. That's part of how we breathe out, right? It's just that relaxation of our muscles and also that force of the lungs kind of bouncing back to their small state. The chest wall kind of bounces as well, okay? So our lungs are elastic, but there's a trade-off between elasticity and compliance. So if they're more elastic, they are going to be less compliant. So that's kind of like the situation that we saw in our arteries, right? Our arteries were really elastic. They held a bunch of pressure in them. So they were less compliant than our veins. So we're saying that same sort of thing here for our lungs. If our lungs were more elastic, they would also be less compliant. That elasticity is due to like the fibers within the tissue of the lung, okay? So they have some elastic properties, but we don't want them to be too elastic because then they would not be able to be as compliant as we need. So another factor that's going to affect lung compliance, which we're going to see varying more often, okay, is the surface tension of the lungs. So one of the things that's happening in your lungs is that there is a little bit of a force for your alveoli to kind of collapse in upon themselves. So the surface tension is due to fluids inside, and this is going to be a force for those alveoli, either to collapse or to resist expanding, because there's a little bit of fluid in there. Okay. So the surface tension is arising because you have some water in the fluid, and those water molecules are attracted to each other. So water molecules are attracted to each other because they're polar, they form hydrogen bonds, right? So that's going way back to the beginning of this class or your previous classes, some chemistry properties of water. So changing the composition of the fluid in the alveoli can change the amount of surface tension. And this does happen over development, like little brand new babies have different amounts of surface tension than adults do. Okay. So we'll be taking a look at that surface tension bit. Okay. But what you want to know is that if you have greater surface tension, what that's going to mean is that you have more sort of water in the lungs, more strongly attracted to itself by hydrogen bonds, which means it's holding on to itself. So it's resisting expansion. It's kind of not wanting to get pulled apart, which means that you would have a less compliant tissue, right? So a less compliant lung, because you'd need more pressure, right? You need more pressure in order to get that to expand, okay? So that's how those two things are linked together, is because that surface tension is kind of resisting that expansion. Right. So to overcome the surface tension from the water molecules that you find in your alveoli, we also have this substance surfactant. So when we talked about the alveolar cells, we saw that our type 1 alveolar cells were forming the lining of the alveoli. They were basically epithelial cells, so cells that form a lining. Okay. So that was one of our barriers for diffusion of gases across alveolar walls, right? If you were any given oxygen molecule, you'd have to cross a type 1 alveolar cell, a basement membrane, and then a capillary endothelial cell, and you'd end up in the plasma. Okay. So the type 2 cells were less common. They're not making up the bulk of the wall of the alveoli, but they do have this important role of helping us to not collapse our lungs and to allow them to expand more easily. So surfactant is basically a detergent chemically. So it's going to decrease surface tension by interrupting interactions between water molecules. Okay. So surfactant is going to have the effect of increasing lung compliance, making it easier to breathe in because it's disrupting these associations between our water molecules, disrupting this hydrogen bonding, meaning that those water molecules don't pull as strongly towards themselves. So we can expand the lung easier, get volume in easier relative to our pressure. And that is just a description of what high compliance means. Okay, so surfactant, this substance that we're about to look at, increases the lung compliance. Okay. So here we see our alveoli. Okay. So thus far, when we looked at alveoli, we were often zooming in on just one specific alveolus. Let me move this to the side too. Okay. But our alveoli are contained in these grape-like sacs. We saw that they have pores between them when we looked at our initial kind of diagram of the airways. So they're connected to each other. There are passageways between them. But not all alveoli are the same size. You have smaller ones, you have bigger ones. So they vary. Now, we need our small alveoli to stay open. We need our large alveoli to stay open. But because of some of our relationships between pressures and radii and tension, this is actually a little bit of a problem for us. So your book has this section on Laplace's law. Fundamentally, what we're looking at is that the pressure here in our alveoli has this relationship where it's related to our tension as well as to the radius of the alveolus. Okay, so what we're looking at here in our smaller alveolus, we're going to imagine a situation in which the tension is the same for each of these. Okay, so let's say, I'm not going to make you do calculations in the future, but I like to do them as an example. So we're going to say, let's make T equal to 2. I can do this on the fly. Okay, so this pressure one here, be 2 by 2. And let's say that the radius here, R1, is just going to be 1. Okay. Okay. So that gives us a pressure of 4. Right. So that would be our P1 for this smaller alveolus. So for this larger alveolus, we're going to calculate out this same sort of relationship between radius and tension to get this pressure. So we're going to calculate out P2 as 2, just a constant, times this constant tension that we're picking for this example. And we'll say that this radius is, let's say it's double. Okay. So we'll give it double the radius because it's bigger. So there, you see 2 times 2 is 4 divided by 2. And we have a pressure, a P2 of 2. So the problem this presents is that we want to remember that our airflow is all based on pressure gradients, right? So if we had this situation, right, where we have a P1, pressure 1 of 4 in this small alveolus, and a P2, the pressure 2 of 2 in this large alveolus, what's going to happen with the air? We see a gradient here, right? Gradient, we're really just talking about a difference, right? So in this situation, this little example, we have a higher pressure over here in this small alveolus, okay, compared to a lower pressure over here in this larger alveolus, just because of this relationship with the radius, just because of this relationship with the size, right? So our air is always going to want to travel from high to low, okay? So in this situation, if we change nothing about that tension, we'd have all the air from that little alveolus move towards that lower pressure in the larger alveolus, okay? And essentially, that means we've collapsed that little alveolus, right? So we're starting to collapse parts of our lungs, collapse all the smaller alveoli, okay? So we don't want to do that. We want our small alveoli to be available to us for gas exchange anyway, right? So we don't want to have this situation where all your air is just trying to find your biggest alveolus and get there because it has the lowest pressure. Okay, so that doesn't work for us. So that's why we need the surfactant. So here we see the situation with the surfactant. So what these arrows are showing us, we have arrows showing these forces to kind of pull in because of hydrogen bonding between the water molecules. So imagine lots of little water molecules all attracted to each other because of their polarity, right? Because that's what water molecules kind of do. Okay. So what we do with the surfactant is we disrupt that, right? We try to get in their way, space them out in order to change that tension, okay? So in this example, what we would see, sharing things over it, okay. So what we would see is that we no longer have a constant T, we no longer have a constant surface tension here, because we have additional surfactant molecules interrupting that force. So in that way, even though we have alveoli of different radii, we could make it so that we have equivalent pressures just by changing that tension, right? So before we had, what did I do as my sample numbers, right? We had 2 by 2 divided by 1 over here. Here we had 2 by 2 divided by 2. Okay, so we had 1 verse 4. Nope, we did not. 4 divided by 2 is 2. I'm sorry. Verse 4. Okay, so we can change the second number. We can change this tension, right? If we lower the tension here on our smaller alveolus, so let's say we change that to a 1, right? So lower the tension. Now we can have the same pressure, even though we have a different radius. Okay. So I'm not going to ask you to do these calculations in the future, but this is what the surfactant is doing. The surfactant, the presence of this molecule, this detergent, the surfactant, is changing the surface tension, changing that pull inward from the water molecules so that we can end up with even pressures in alveoli of different sizes. Okay. So this can be a problem in premature babies who are not yet able to produce enough surfactant, because if you can't produce enough surfactant in order to disrupt that surface tension in the small alveoli, they are going to follow this first model and kind of collapse into the larger ones. Okay. So that was related to our compliance because that surface tension is resisting the expansion. If we have something resisting the expansion, we're essentially decreasing compliance. So now we're going to move out of the alveoli and that lung tissue, and we're going to think about our airways. So for our airways, there are a series of tubes. So they are also going to affect our ventilation because we're going to see that we can have differences in resistance in those tubes, essentially. Okay. So we had our, when we're talking about airway, right, we had our nasal passages, our oral passages leading into our pharynx, our larynx, our trachea, right? Then our trachea is splitting out into the primary bronchi, the secondary bronchi, the tertiary bronchi, and then eventually into our various bronchioles, eventually leading us into the respiratory bronchioles and the alveoli. So we're talking about these tubes that are getting us to the alveoli. That's what we're talking about when we're talking about airway. Okay. So our airway are getting smaller as they get towards our alveoli. Okay. Smaller things have higher resistance, but overall, because of this increasing in branching, they're going to keep the total resistance in the lungs low. This is like when we talked about our total peripheral resistance in the arterioles, right? We talked about that we were just like adding up all the resistance in all of them, right? So this is a similar kind of thing. Or like when we thought about our capillaries, how they spread out so much, even though they're teeny, teeny, tiny, because there are so many of them, our overall resistance stays low. So because we have all those splits from the primary, secondary, tertiary bronchi, then all into all our little bronchioles, we don't have too much resistance that we usually need to overcome in order to breathe. However, we do need a pressure gradient for airflow, right? So we know that we are comparing our pressure in our alveoli versus the pressure in the atmosphere in order to move air, right? So whichever is higher is where the air is going to leave, whichever is lower is where the air is going. Okay. Usually resistance in the airways is pretty low. Okay. You increase the resistance, you are going to make it harder to breathe because of our flow rule, right? So our flow, right, was dependent on our difference in pressure divided by our resistance, right? So if you increase the resistance, right, if you wanted to keep the airflow the same, you would also have to increase equivalently that pressure difference, right? So that would keep the flow the same. Otherwise, if you increase resistance, you end up decreasing the flow because you're dividing by a higher number. Okay. So when we see changes in resistance, if we increase resistance, it's going to make it harder to breathe, essentially. You're going to need to put in more effort if you want to keep getting enough air into the lungs. Okay. So this is usually going to lead us to need a pressure gradient of more than 1 millimeter of mercury, whereas under normal conditions, you only need about 1. Okay. So our next diagram is showing us that situation. Right. So when we look at this, what we're looking at are our intraalveolar pressure. Right. So that is our PALV, our pressure inside the lung. Okay. And we know it's relative pressure to the atmosphere. So under all of these examples, our pressure in the atmosphere has been set to 0. Okay. At the bottom, we're looking at how much air we're breathing in. So physically, how much air is in the lung. Right. So what we see here is first our inspiration, breathing in, and then our expiration, breathing out. So under a condition with normal resistance, right, you can see both these examples for the normal resistance and the increased resistance. We're looking at an example where we're saying we want the same volume of air, right? We're not going to change the volume. We're just going to change how hard we're working to get that volume. Okay. So with normal resistance, you only have to drop down to an intraalveolar pressure of -1, right? That's going to be sucking the air in, right? Sucking us towards that lower pressure, lower than 0, -1. Our atmospheric pressure was 0. Okay. So air is moving into the lung as you do that. Okay. And then just smoothly, as your pressure goes above 0, as you have gases moving in, right? It's going to go up to about 1 and then back down as you're breathing out that air. Okay. So that's our normal situation. If you have increased resistance, so you're going to see increases in resistance. You're going to predict what I'm about to say. When you might see an increase in resistance, think about your guess about what's going to happen to the tube. Right. So in some way, we're thinking about an airway that got smaller, right? We saw a decrease in radius, creating an increase in resistance. Right, that's a relationship that we're usually focused on in physiology when we're thinking about resistance. Okay, so we're going to see changes to the shape of that airway, or maybe the mucus layer on it could functionally make it feel narrower. Okay, so increases in resistance mean that in order to have that same flow, the breath volume, right, essentially is our flow. We want to keep that the same. All right, so we're going to have to raise our pressure difference in order to combat that increase in resistance. So that's what we're tracing in this top diagram, this increased resistance. We're saying that with this greater resistance, we now need to have a greater difference between our alveolar pressure and the atmospheric pressure in order to pull in the same amount of air. Right, so here we see our example is going down to -2, right? Just to get that same breath volume. And then to expel it, we also have to have a greater difference. So we're going up to +2 here, just to get that same volume of air. So you would potentially physically be able to see that someone is working harder to breathe because of this increased resistance. Okay. All right. So we're going to think about the factors that can affect that resistance next. So one of the factors, or two of the factors are passive forces. So two of the factors that affect our overall resistance in the airway are changes in the transpulmonary pressure during the respiratory cycle. The respiratory cycle is just that inspiration, then expiration piece, right? You breathe in, then you breathe out. That's the respiratory cycle. That transpulmonary pressure was that pressure, that distending pressure across the wall of the lung, that alveolar pressure minus the intrapleural pressure. Okay. So that transpulmonary pressure does cause our lung to change size and shape. So in a way, we are affecting resistance, right? If you think about the bronchioles traveling through that tissue, right? As we have changes in transpulmonary pressure, when it increases, it's making the lung bigger, expanding it, okay? And then the opposite would be true as well. When it decreases, the lung is collapsing back down. There are also tractive forces. So like think traction, like pulling. So tractive forces are just forces of tissue essentially pulling on your airways. So our transpulmonary pressure is a pressure across the lungs that kind of pulls open our airways. The tractive forces, think like ligaments and stuff like physically attached to the airways that are also kind of opening those airways as they move. Okay. So as tissues move away from airways, they have the effect of pulling the airways open. So those are things that are going on kind of all the time, those passive forces. But the things we're going to see varying a bunch are going to be the contractile activity of smooth muscle, as well as our mucus secretion. So we want to remember when we're thinking about the wall of an airway, or the wall of most things in our body, right? So we have our tube, but if we were to cut across it, right, we're going to see that we have rings of smooth muscle, and a lot of them that can contract and therefore constrict, or relax and expand. So that's going to be true about our airways, like it was true about a bunch of our blood vessels. The difference that we think about here with the airways, excuse me, when we're talking about the structure of the airways, we mentioned something called the mucus escalator, right? So we know that our airways are coated in a layer of mucus from goblet cells that is like essentially a sticky fly trap trying to catch pathogens. And then we have ciliated cells that try to brush those pathogens up and out your mouth. You could cough it out, right? So you've all, I'm sure, had the experience of being sick, having some congestion, having that thick mucus in your airways, right? So essentially here, you got a lot of mucus. You kind of make that tube narrower briefly, okay? Or at least you leave that tube narrower when you thicken that mucus layer until you get rid of the mucus. Right. So we're thinking about smooth muscle changing the size of our airways first. Okay. So this is going to happen in terms of radius, size, shape, the same way it did when we were talking about our vasculature. We're going to see some slightly different effects of nervous system and gases here, but the fundamentals are the same. So now instead of talking about vasoconstriction and vasodilation, we're just going to talk about broncho for lung constriction and bronchodilation. Okay. So in bronchoconstriction, okay, we're talking about our bronchiolar smooth muscle, right? So those airways going into the lungs, those bronchioles, have layers of smooth muscle. When that smooth muscle contracts, makes that passageway narrower, means our radius has decreased. We have an inverse relationship between radius and resistance. So when we have a little narrow passageway, we have higher resistance, and therefore we're either going to have less flow or we're going to have to exert more pressure to have the same flow. So in bronchodilation, right, it's just the opposite, just like vasodilation was the opposite of vasoconstriction. So that smooth muscle, if it relaxes, your airway gets bigger, tube gets bigger, radius goes up, resistance goes down. Okay. So we're thinking about those same properties that we're trying to change when we're thinking about changing airway resistance. So it's that contractile state of the smooth muscle in the bronchioles that is going to be under the control of local factors, which are our intrinsic controls, as well as factors from things out in your body, chiefly nerves, hormones, right? So extrinsic factors are also going to be able to affect that smooth muscle and how contracted versus how relaxed it is. So we're going to start with the extrinsic control. Okay. So when we're talking about the extrinsic control of bronchiolar radius, we're talking about the autonomic nervous system. Okay. So the autonomic nervous system is just our sympathetics and parasympathetics. Okay. So when we have these two parts of the system active, we're going to be able to change the relative dilation or constriction of our airways. Okay. So this time we actually do see the parasympathetics involved in working on that smooth muscle and the state of our bronchioles. Whereas when we were talking about our vasculature, we were really focused on, is the sympathetic nervous system active or not? Okay. So now we're going to be able to change in both directions. Okay. So if we have our sympathetic nervous system active, our fight or flight, right? So fight or flight, you're running away from something, you want to breathe, right? You want to get lots and lots of air to fuel blood going to your, to fill the blood going to your muscles with nice juicy oxygen for them to use to get lots of ATP. Okay, so you want lots of air, which means you want to increase the radius of your airway, right? You want a nice big wide tube, low resistance, lots of flow. So under sympathetic control, you're going to see bronchodilation. So you're going to see an increase in the radius, which is the result of relaxing smooth muscle. Okay, so if your sympathetic fight or flight nervous system is on alert, you're going to open up those airways. Okay. The parasympathetics, that rest and digest, you're not going to need as much airflow, right? You're not going to need to see that huge increase. So this is when we'll see bronchoconstriction. This is just going to be the opposite of that situation. All right, so we'll see potentially a little bit of narrowing of the airway, that parasympathetic. Okay, so this is when we see our contraction of the smooth muscle. So since it's a circle, the muscle is a circle, right? If that loop gets shorter, you have a smaller radius. Okay, contraction, bronchoconstriction. So our extrinsic control, okay, is also under some effects of hormones, right? So we have some hormonal control. Really chiefly, we think about epinephrine. Okay? Epinephrine, like our sympathetic nervous system, very tied into our sympathetic nervous system, is going to relax that smooth muscle and cause bronchodilation. Okay, so our additional factors, epinephrine is just going to work kind of like our sympathetics, as it often does, right? So it can make us go from a little tube to a bigger tube. Okay, so epinephrine, adrenaline, same thing. You want to run away, stressed out, you want to breathe a lot. So the next thing that we want to think about is intrinsic control of bronchial radius. Okay. So when we think about intrinsic control versus extrinsic control, whenever we're thinking about intrinsic pathways versus extrinsic pathways, intrinsic means of the thing itself, right? If you have intrinsic qualities, they're your own of yourself. Okay, so intrinsic control of bronchiolar radius is going to have to do with local factors right there in the tissue surrounding the bronchioles. Okay. So often this is going to have to do with the gases that we're going to be tracing as we think about gas exchange. So I'm just going to point out that bottom bullet point first, actually, which is that a bunch of carbon dioxide building up is going to cause bronchodilation. Okay. So when you think about carbon dioxide, what you want to be thinking about, right? Carbon dioxide is a byproduct of metabolism, right? So you have tissue working, trying to produce a bunch of ATP. We're trying to get rid of our carbon dioxide, okay? If you have a bunch of carbon dioxide kind of building up, right? That means you're not breathing off enough of these waste products. So to breathe out a lot more of this waste product, this carbon dioxide, to get rid of it, you're going to want to open up those airways more and increase the ventilation, essentially, increase that sort of airflow in and out so that you can get carbon dioxide out of there. So carbon dioxide, we're going to see when we talk about gas exchange, is one of the things that your body is really carefully regulating how much carbon dioxide is in your blood. Okay. So carbon dioxide is going to be a trigger for bronchodilation. And the way I like to remember that is by thinking about the fact that we want to get rid of carbon dioxide. And if you want to get rid of a gas, make the airway bigger so that you can have more flow. The more potentially relevant to your daily lives that you might notice is histamine. So histamine has a local effect. So histamine, we saw before, is related to inflammation. Okay. So histamine is going to be released during asthma, during allergies. It's a sort of inflammatory thing. It also increases mucus secretion. And overall, the effect of this chemical is bronchoconstriction. So kind of everything it's doing. If you think about like asthma, allergies, inflammation, I like to think about histamine as like, it's kind of an immune response, right? So think about histamine as it's reacting to you breathed in something that your body saw as a threat, right? So it does not want you to keep doing that, right? It wants you to stop breathing in whatever this threat is, right? So it's going to constrict down those airways so that you don't breathe in more of it. Okay. At least that's how I remember this, right? So histamine is going to cause bronchoconstriction, cause a narrowing of the airways. There are also pathological states or diseases that increase airway resistance, usually increase. Okay, so we did mention asthma before related to histamine, but asthma is technically actually a disease kind of the smooth muscle of the bronchioles. So in asthma, I'll look at the bottom here. Right. So here we're looking at a normal airway versus an asthmatic airway. So one thing we can already see in the normal state, in this relaxed state, is that we have some differences in that wall of the airway. So here we can see what this depiction of a normal layer of smooth muscle is in this bronchiole. First, we can already see that our wall is a little thickened and potentially inflamed here in this asthmatic airway. So we can see kind of more of this smooth muscle here. Okay? But the thing that's actually happening during an asthma attack, right, is that smooth muscle is tightening when it shouldn't be. Okay, so here we can see that we have someone breathing some stuff in, it's causing an asthma attack. So we're having that constriction down of that airway, causing a much smaller radius, and therefore it is much more difficult to breathe, okay? Versus this big normal airway where we have a nice big radius.
What's that little gas?
Which look, I think it relaxes it. I think so, yeah. Yeah, because you can imagine, right? Like if you relax that muscle, it gets big again. Right. So another disease that you'll see related to airway resistance is chronic obstructive pulmonary diseases. There are a bunch of them. We refer to these generally as COPD, and we'll be looking at them as we look at our like lung volumes and some stuff in the next couple slides. Okay. So first we are going to talk about the lung volumes and lung capacities and some of the ways we're going to kind of measure some pulmonary function. So the old school way of measuring lung volumes is by having someone hook themselves up to this spirometer. That's a device that measures this lung volume. So we can see that they have a bell of air that they're breathing in and out through this tube system, through their mouth, not their nose. This is attached to this kind of pulley system and a pen. So we essentially have like a transducer that's creating this output. Okay. We don't really use a device that looks like this anymore, but that's functionally kind of what's happening anyway. Okay. So this is spirometry, a spirometer, just something that measures your lung volumes. Okay. So the volumes that it's measuring are actually a bunch of them. Okay. So when we talk about lung volumes, we're going to really break up whether we're talking about the volume of air you're breathing in, the volume of air left in your lung after you've breathed out. We're going to test big breaths, big inhales, big exhales. So we're going to be able to compare a lot of different kind of properties of the lung this way. So everything together is going to add up to our total lung capacity, okay? But we're going to break this out by a lot of different pieces, okay? So what we're going to see when we're just breathing normally and easily is the tidal volume, okay? So the tidal volume is just the amount of air in one unforced breath, so easily breathing just normally. So that's what we see happening here, are our normal tidal breaths, okay? So in and out, those 500 milliliters, okay? However, you are not completely emptying your lungs every time you breathe out, especially not with one of these easy tidal breaths. You're not breathing in all the new air you could possibly breathe in every time you breathe in, right? We're not like collapsing our lung and completely re-inflating it every time we breathe. Okay. So we have a lot of other sort of volumes we could measure in the lung. Okay. So if we're not breathing just easily, right? Like we're not just measuring tidal breaths, we might want to know, okay, what is the maximum that we can still breathe in? So if you breathe in an easy tidal breath, you might then be instructed to breathe in a really deep breath. Right. That extra amount above the tidal breath that you breathe in here, this part, this is your inspiratory reserve volume. Okay. So inspiratory for inspiration for breathing in, reserve, it's like the extra, like it's on reserve, like you could breathe in that amount if you needed to, but you usually don't need to when you're relaxed. Okay. So that inspiratory reserve volume is usually about 3,000 milliliters. So like way more than a tidal breath, right? So you can actually breathe in a lot more than you do when you're just sitting around easy breathing. So that's our inspiratory reserve volume. Now we have the opposite as well. So we also have an expiratory reserve volume, okay? So if you breathe out easy and then you go breathe out all the air you can breathe out really hard, okay? That's going to be your expiratory reserve volume. So you started at the end of expiration, and then you breathed out even more, okay? That is going to be our ERV, okay? So expiratory, expiring, okay? Reserve, It's like extra. So the extra amount you can breathe out is about 1,000 milliliters. Your lung is still not collapsed and totally empty after you breathe all the way out. There is still going to be some air in your lung. That's good because we don't want our lungs to totally collapse. Okay. So that is going to be our residual volume. So residual is the amount left over, right? So the amount left over, the volume left over at the end of that deep breath out is your reserve volume. Okay. So this is going to be about 1,200 milliliters. So you would not be able to measure that reserve volume with a spirometer, right? Because the spirometer is only measuring what did you breathe in, what did you breathe out. You could measure it by changing the properties of the gas. If you mixed it in with some helium, you could measure how much of that helium is moving, basically. But these other ones you would be able to measure with a spirometer. Okay, so we'll stop there for today. And next time we'll practice with this a little and then talk about lung capacities and some lung function tests. Okay, so for now, just know that we were just talking about lung volumes here.